So thanks so much to Jan for inviting me to this. I'm Hannah. I'm just finishing up my PhD at UCL, soon to be a fellow at ESO in Chile. And actually this work was done when I was a visiting student at ESO Germany. So to start with, hopefully I don't need to convince anyone here that precise mass measurements are really essential for things like atmospheric characterization. And also, by combining mass and radius, we can estimate compositions of exoplanets. So that's really great in theory, but how do we go from our RV observations at a telescope to finding an actual planet mass measurement? Well, there's quite a few different steps we need to take in between, some different things we have to account for, some different questions we have to answer. So these are things like, what data reduction pipeline am I going to use? How will I account for offsets between different instruments or different telescopes? What kind of modeling toolkit am I going to use? There's lots of different ones available. How do I choose which one? Does it make a difference? Do I allow my planets to be on eccentric orbits, or do I force them to be circular? And what difference does that make? What kind of priors do I put on the parameters in my models? And how do I mitigate for stellar activity? Do I use things like a GP? And if I do, again, which type of GP might I choose to use? And the point I'm trying to make here is that all of these different choices are going to influence the planet mass that we find. And what that means is that if we go to the NASA Exoplanet Archive, which is a fantastic resource that we definitely all use, I'm sure, if we go to a single planet, we might see that there's multiple published mass values. So here I'm showing just one single planet on the archive. And you can see that the published masses vary from just under 5 Earth masses up to over 10. And what's, I think, particularly interesting about this case is that all of these are what we might consider to be precise mass measurements. But how do I decide which one I should use in my analysis? And what if I wanted to do a population study? Is it okay to use masses that come from completely different sources and might be very different from each other? So to try and kind of counteract this, we decided that we were going to do this kind of consistent analysis of planet RVs to get a set of masses that have been found in a homogeneous way. So first of all, we had to do our sample selection. So we went to the NASA Exoplanet Archive and we found all of the confirmed small planets. Of course, you could do this for any size of planet. We focused on the small ones because we didn't have time to do all of them. And also we thought that the small ones might be the most affected by these kind of issues. We then had to choose some data to use for this. So we chose to use the HARPS archive. So HARPS has been observing exoplanet RVs for more than 20 years. It's got a huge data archive, most of which is publicly available. And so we took the entirety of the HARPS data archive. We removed any of the low signal to noise observations, and we said we need at least 50 observations per target. And that was because we wanted to test some GPs. And then we took this list of HARPS observations, we took the list of the NASA confirmed small planets, and we cross-referenced them to find 87 small planets which have been observed by HARPS with at least 50 observations. So the idea was that we'd take these 87 small planets, get their RVs from HARPS, fit them all completely consistently, and then we would have this fairly good-sized sample of planets that had been found homogeneously that we could then do some analysis on. But in the process of kind of coming up with this project and the idea, we realized that we didn't just want to do one consistent approach to modeling the RVs for all of these planets. And that's because, you know, as a community, it's not super obvious what the best way to model RVs is. And so we wanted to see what impact it actually had by making some of the different choices that I mentioned at the beginning. So to make our lives slightly more difficult, we actually decided to run 12 different models for every single target. So that does mean I have over 1,000 individual planet mass measurements. But the reason we did this is because we wanted to test a few different things. So we wanted to see if adding things like a long-term trend parameter to our model made a difference. Whether that trend parameter was linear or quadratic, did that also make a difference? What about if we fix our orbits as circular or allow them to be eccentric? How does that impact the mass we find? What if we add a GP to mitigate stellar activity, or if we don't add one? And then if we do add one, what dimensionality of GP? And by that, I just mean, is it modeled on just the RVs, also RVs and activity indicators? And if we do that, which activity indicator do we use? So we did all 12 models for all 87 targets. And before I get into results, I actually just want to go through some caveats. I think this is really important when doing these kind of big kind of archival analysis, is to mention that archival data can be very challenging to work with. The way that the HARPS archive is organized has not always been consistent. I have to say, in general, the ESO archive is great, but 20 years ago, the consistencies in naming convention weren't as good as they are now. They're still not good in a lot of exoplanet cases. And so it's possible we might be missing some observations, some targets, and things like that. Another thing to note is that we did not rerun the data reduction pipeline. There's two reasons for this. One is that it would take a really long time, and this project already took a really long time. And the second is that there's actually a new HARPS data reduction pipeline, and another team has already said they're going to re-reduce all of the HARPS archive at some point and make it available. Another thing I put was that we have no control over observing strategies. So as we just heard from Chris, it can make quite a big difference if you have a very different observing strategy. And that's actually something we kind of saw in our analysis. Mostly we could see kind of the impact it had if there was a large gap between observing seasons and things like that, particularly I think in cases where a single target was observed in multiple programs, where they obviously maybe didn't know what other teams were doing, or weren't sure what the specific science use case was for those other teams. And then the other thing to note is that because we wanted to do everything consistently, we used the same stellar activity mitigation, i.e. a GP, for all of the stars in our sample. And that is, I said might not, but probably not optimal, in that we didn't adjust our GP kernel or anything if it was an M dwarf versus an FGK star. I think that's something that could be really interesting to look at in the future, but it's not something we did in this work. Okay, so now I can show you some results. Just to warn you, this plot is quite big, but I will explain what's going on. So first up, just look at the x-axis. So this is all of the planets in our sample. So they're labeled by their tick ID and then the planet letter. On the y-axis is the radial velocity amplitude we find in our model in meters per second. The reason we do RV amplitude, not mass, is because we don't want to add in the addition of the uncertainties from the stellar mass. And then finally, the data points you can see are for 3 of our 12 models. So here we're comparing the difference between not adding a trend, adding a linear trend to the model, and adding a quadratic trend. And it's a little hard to see because there's so many points on here, but hopefully what you can notice is that in most of these cases, so for most of the planets, the 3 models basically overlap. So it seems that when doing this big analysis, even if you add a long-term trend parameter to your model, whether that's linear or quadratic, in most cases, it's not going to matter to the planet mass you find unless there's actually a trend, which is quite reassuring. So if you want to add a trend parameter to a model, it's probably okay. So what about some of the other things that we looked at? Well, next is the GP. So this is even slightly more complicated than the last plot. So again, we have all of our planets along the x-axis. On the y, we have our RV amplitude. This time we're showing 4 different models. Okay, so the pale blue triangles are a no GP case. The green circles are a one-dimensional GP, so modeled just on the radial velocities. The yellow crosses are 2-dimensional, so it's modeled on the RVs and the forward to HARP maximum. And the red diamonds are the 3D, so that's forward to HARP maximum and the bisector inverse slope. So here you can see that there's a little bit more difference between the different models. So it's a little hard to tell in this big plot, but what we notice is that the no GP case is the most different, which is what we would expect. We also see that the uncertainties are reduced for the cases with a GP. We notice that for some systems, you don't necessarily need to add a GP. They're not particularly noisy systems. And the other thing we notice is that the 2D and 3D GP give more consistent results in RV amplitude than the 1D GP case. So if you're going to use a GP, maybe it's a good idea to model that with an activity indicator, so a 2D or 3D one, rather than the 1D case. Now, we're not saying that the 1D case is wrong, but it just from our analysis seems like the 2D and 3D are more consistent. Okay, and then finally, I wanted to show you the impact of eccentricity. And what we ended up doing actually was doing 3 separate models for this. So we ran everything fixing it as circular. We then allowed our orbits to be eccentric, and we put a prior on the eccentricity that was basically just uniform. So allowing it to vary essentially between 0 and 1, although we did parameterize it, so it wasn't exactly like that. But when we did that, we noticed that we were getting some pretty high eccentricities. So we decided to do a third option as well. And this was where we allowed the eccentricity to vary, but we put a prior on it that was in the form of a beta distribution. So I'm going to show you the results of that now. Okay. So in this case, the circular is the pale blue triangles. The uniformly distributed prior on eccentricity is the green triangles. And the purple squares are the kind of beta distribution prior on the eccentricity. So in this case, you can see, hopefully, that actually there is quite a big difference. In some cases, the RV amplitude we find is actually significantly different, depending on whether you have a uniform prior on the eccentricity or a beta distribution prior on the eccentricity. In some cases, although it is consistent, i.e. within error bars, the actual median value is maybe a factor of 4 higher between the different models. And although, yes, being within 1 sigma is great, but when we're actually doing the analysis and we're looking at compositions, we're looking at atmospheric follow-up, we're using the median value. So that is still really important to be aware of the difference that can make. So depending on how you model your eccentricity, it can change the amplitude of the RVs by up to a factor of 4. So if you're going to allow the eccentric bits, which you probably should because physically it makes more sense to do that rather than fix them as circular, we would suggest using some kind of physically motivated prior on those. So whether it's a beta distribution or something else, that's kind of requires a bit more investigation, but we definitely think that using some prior is a good idea. Okay, finally here, I just wanted to show a little comparison between what we define as our best model for our individual planets versus the default published on the NASA Exoplanet Archive. So you can see that in some cases they are very much in agreement, which is great and quite reassuring. And in some cases, they are not so much in agreement. So a few over here and a few over here. And this isn't to say that any of the ones on the NASA archive are wrong, absolutely not. But what we're saying is that if we want to do this big kind of group comparison, it's a good idea to do it in this consistent way. One other thing I wanted to show is just a couple of histograms. So on the left here, we're showing the RV amplitude uncertainty for the default published again in gray, and then for our best model in blue. And what you'll notice is that on average, we have a higher uncertainty. And this doesn't mean that we're unhappy with our results in any way. We weren't trying to get the most precise mass measurements for each individual planet. Instead, it was more about getting the kind of overall accuracy of the sample to be as good as we possibly could. And on the right-hand side, you can see the RV amplitude difference from the default published. So literally what amplitude we find, subtract the default published value. And there's a couple of things to note here. So in some cases it's up to 5 meters per second different, which is quite high. The majority is centered around 0, but maybe slightly offset, which is kind of interesting. But again, it's, I think, a good example of how it does actually make a difference depending on the model choices. Okay, so just a couple of takeaways. The modeling choices do make a difference in your extracted RV amplitude, up to a factor of 4 in the cases that we tried. Eccentricity in particular has a really big impact. So if you're going to allow for eccentric orbit, probably use a physically motivated prior. GP does also have an impact, although not as much as the eccentricity. And we find that the multi-dimensional cases are more consistent than the GP's model on just radial velocities. I'm going to actually skip the summary and go to an extra slide because I just wanted to give you a little kind of sneak preview of the second paper in this work. So we're currently just finishing writing this up now, but where we've taken these RV amplitudes, we've done a homogeneous analysis of the stellar parameters and combined them to get some new little kind of exoplanet masses to then look at the radius valley in terms of mass and radius. So this plot is just showing the sample of our planets that are orbiting M-dwarf stars, split into their location relative to the radius valley, and then we can investigate kind of the compositions of these planets and whether they match what we expect for being above, below, or inside the valley. And again, for the FGK stars, we've done the same thing. When this paper is out, hopefully quite soon, or at least it will be submitted quite soon, we're going to show these comparisons, but we're also going to give a list of kind of top candidates for atmospheric follow-up. So in particular, ones that are inside the valley and have a potential water-like composition or a potentially unusual composition. So do look out for that in the next few months. But otherwise, I'll go back to my summary. Do have a look at the paper, or the first paper of this work, which has all of the radial velocities and goes into a lot more detail about our analysis and how we did this. Otherwise, I'm happy to leave it there and take any questions. Thank you.
Very good. Thank you so much, Hannah, for an excellent presentation. Questions from the audience? Chris.
Hi, Hannah. That was a great talk. I was wondering if you could comment on whether you think that that offset in that histogram slide, in the difference between like the default RVs and your RVs, is significant enough to say that it's like there's like some kind of systematic bias.
Do you mean in this one on the right-hand side?
Yeah, yeah.
Yeah, so it's not super significant. So I certainly in the paper didn't claim anything was super significant. It wasn't obvious to us that there was a particular bias either way. Like, although in this plot it looks like there's a slight shift. So as part of this, we did manually check every single posterior distribution for each model for each planet. And we did have to remove a few that looked a little bit questionable, and the details of that in the paper. But I think it wasn't obvious that like, oh, it's all of the really small planets are bigger when we do it this way, or smaller when we do it this way, or it's all of the ones that are around M dwarfs or FGK stars, or it's the ones with the most observations have a higher blah 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 or something. So we did try and compare this to other parameters and see if there was a link, but we couldn't find any really obvious ones. But it is tricky given the differences in the observing programs. I think it's hard to really say definitively.
Thank you.
Other questions for Hannah? Well, people ponder for a moment. So you made what seems like a very sensible choice early in this, which was to only use data from HARPS and kind of remove one more axis along which things can vary. Even within a single instrument, I'm curious if you considered things like different instrument noise properties for HARPS, just because it's been running for so long. There have been some interventions along the way, the fiber upgrade that happened a decade ago now. So is that, are there allowances for either different amounts of, jitter in the RVs or things like this in response to either the era of HARPS, so to speak, or to the types of stars you're observing?
Yeah, so we did. So we actually modeled it as two separate instruments, pre and post fiber upgrade, which is kind of the typical approach that people use. And we included a jitter term for both. So yes, it was accounted for. I don't know if it's necessarily the best way of doing it. I think there's, a lot we don't fully understand about instruments and systematics over very long baselines. I think what would be interesting, and actually what I'm planning to do, kind of moving into my fellowship, is to compare some of these systems where they also have data from other instruments. And I think that would be really nice to do a comparison of, does it make a difference, particularly if they have espresso data, because the new reduction pipelines are the same, essentially, as much as they can be for HARPS espresso. And so maybe we could see, does having the higher precision with espresso change the mass of the planets? And or, does just having data from different instruments show a really different, distribution? I think there's a lot of work we can do looking at the kind of bigger picture and sharing data between different instruments. I think, I'm based in Europe, so I use a lot of ESO instruments, but I think working with some of the US teams to look at how does it vary, if we have some of these planets have also been observed by US instruments, does that also make a difference? I think could be really valuable.
Yeah. I think there's a lot of interest in more like coordinated campaigns using multiple facilities. So this type of work is very interesting. Okay, any other questions from the audience that people would like to raise? Okay, well, if not, let's thank both of our speakers again for giving excellent presentations on their recent works. So thank you very much to Chris and Hannah for calling in and giving these great talks. I didn't mention this earlier. I meant to. We're not going to have a colloquium next month because it's the Thursday just before EPRV 6, and I think enough people are either prepping for the conference or traveling that we're just going to scratch that one. We'll see many of you hopefully in Porto, but we will resume in July and kick off the summer portion of the series. So thank you everybody for calling in. It was great to see you, and I'll catch you in a couple of months. Take care until then.